Okay, so I hope you can see the shared screen.
Yes, sir.
Yes, sir. So in the previous lecture, we discussed about how to calculate data density along the flight line. Okay, so we have derived the equations for calculating data density along the scale line as well as across the scale line. And we have also established relation for the uniform kind of data density. If you want to get a uniform data density, so to get uniform data density, there is a requirement. The point spacing along the scan line should be equal to point spacing across the scan line. Okay. So if we have it's a two successive points, and this is along the scan line, and this is the across the scan line. So this gap should be equal to this. Okay. And we have also seen that the line density which is estimated, if it is along the scale line, so density along is equal to, let's say if this spacing is delta x, so it is equal to 1 divided by delta x. Okay. And let's say if this spacing is delta y and this direction is across. Okay. So density across the scale line is equal to 1 divided by delta y. So the line density which we estimate, actually it gives idea about like how many points we have per unit length. Okay. So in this case, you are moving from one point to the next point. So so what is the gap between two successive points? If you take inverse of that, you will get a data density, line data density. Okay. Now we'll see the radiometric analysis of laser beam. In case of laser pulse, you have already seen that like a laser pulse, how much energy is there within a laser pulse. Okay. So laser generates laser pulse that is filled with quanta, and a particular fixed energy is within the laser pulse. Okay. This is the peak amplitude, AP. Okay. So corresponding to peak amplitude, let's say we have a peak power. Peak power within a laser pulse, if it is there, then the energy is calculated as peak power into TP. Who will tell me what is TP over here? Corresponding to peak amplitude, we have a peak power.
So pulse width.
Yeah, this TP is the pulse width that is calculated at 50%. Okay. So this line is 0.5 AP. And this is pulse width TP. What is a typical value for TP in case of laser scanning?
10 nanoseconds.
Correct. It should be in the order of 10 nanosecond. Okay. So this TP should be in order of 10 nanosecond or less than that. So if it is in order of 10 nanosecond, then what is the distance covered by this pulse in the space? So this
3
distance,
meters.
it will be 3 meters. Correct. It will be 3 meters because this laser pulse is traveling with the speed of light. So then distance traveled by TP, this pulse with TP is equal to 10 into 10 to the power minus into 3 into 10 to the power 8. So it is why it is 3 meter, is it? 3 meter, correct. Okay. So energy within the pulse is calculated by the peak power into TP. Okay. So one more parameter we define over here, though this laser pulse, this various laser pulses are generated at a particular rate. Okay. So it's a periodic signal where we have a laser pulse, and next laser pulse is generated at fixed interval that is defined by time period TP. It's sorry, this time period T. So this is time period T, and the pulse firing rate is equal to 1 divided by T. Right? We have calculated energy within this pulse. Okay, and that is E. We have calculated it peak power into TP. We also define, if we consider this signal as a whole, here we are doing the analysis for one particular laser pulse. Okay. For this laser pulse, we are doing the energy based analysis. If we consider this entire signal, periodic signal, then what in that context, which energy parameter we define over here? There we'll calculate first this average power. Okay. Further, we'll calculate the average power generated by the laser beam. It's which has a continuous laser pulses which are fired at a particular interval. Okay, fixed time period. So P average, what it will be? E is the energy within a pulse. If we want to calculate average power of this signal, this periodic signal, so what will be the average power? Energy generated per unit time. So it will be this E divided by time period T. Okay. So energy, what is the energy complete? Now you need to consider this complete signal. Okay. So entire time period, how much energy is generated? So E divided by T will be the average power. Okay. Now you need to select this envelope, complete this. If it is a periodic signal, then this is the it's a unit signal that is repeated after T interval. Okay. So E divided by T will be the average power, and E we have already calculated from equation 1. So you can write from equation 1, it will be peak power into Tp. 1 by T you can write it's a pulse firing rate. Okay. So it means for a given average power, if average power is given, okay, higher the pulse rate, lower the pulse energy. If this P average is fixed, it is given. If you increase the pulse firing rate, okay, it means energy within a pulse will decrease. Okay, and it means for a given pulse duration, in this case, for the given pulse duration Tp, the peak power should also decrease if pulse rate increases. Just see, if this is average power is given, okay, then if you increase this pulse firing rate, and if Tp is also given, let's say it is given 10 nanosecond, then what will happen? This peak power will decrease because this parameter is given, we are considering it constant. Okay. So for an example, if certain like a set of values are given for these parameters, like let me first erase this. Okay. So if let's say average power is given 0.2 watt, okay, and this pulse width Tp is also given, it is equal to 10 nanosecond. These two parameters are given. Okay. And one additional parameter is also given, that is peak power of a pulse. P peak is also given, it's 2 kilowatt. So calculate this. What should be the pulse firing rate maximum that can be attained? solve this.
Sir, 10,000 hertz.
Okay. All of you, please solve it.
Yes, sir. 10,000 hertz.
What's about the rest of you? बाकी लोगों का कितना आ रहा है?
Same, sir, 10 kilohertz.
Bhagat, could you please unmute?
Yes, sir.
सॉल्व किया आपने?
Yes, sir. नहीं हो रहा था.
Did
Sir,
you attend?
my answer is 10 kilohertz.
I'm coming back. Did you, Bhagat, did you attend the previous lecture?
Sir, no, sir.
Regular रहिए आप क्लास में, ठीक है ना?
Yes, sir.
Otherwise, it will be difficult to catch up the concept, ना?
Yes, sir.
Okay, please mute and try to solve this.
Okay, thank you, sir.
Subham, have you solved this?
Yes, sir.
कितना आ रहा है?
10 to the power 4, 10 kilohertz, sir.
It's 10 kilo. It's very simple. Formula is given there. Just you need to substitute the values. So this equation, in this equation, you need to going to just fill the values. So P average, it is given 0.2 watt. So you can write it 2 into 10 to power minus 1 watt. It is equal to peak power is given 2 kilowatt. TP is given 10 nanosecond. Now it is equal to PFR. So this pulse firing rate is equal to 10 to the power 4. Is it? And it is in 10 to the power 4 hertz you will get. So it can be written as 10 kilohertz. So similarly, like a different combination can be given. Let's say if peak power is fixed, some 2 kilowatt, calculate P average. So it comes out to be 0.2 watt, like that. Okay. What is the interpretation you have? What is the physical interpretation of these values which we are putting over here? Because these values are taken from the real system. You see, average power is very less. P average is only 0.2 watt, while you see the peak power is 2 kilowatt, very high. So very high peak power can be generated when this like this. Okay, so I talk about peak power. Very high peak power can be generated when this pulse length, you can also say pulse width TP, if it is very less. Okay. So while just see the average power is only 0.2 watt. So it means this, if we consider the time this TP, and like if you take this is TP over here, and the rest of the time to complete the entire time period T, let's say if you talk delta T, so delta T will be equal to capital T into TP. This time is very high compared to this TP. If you increase this time, it can be increased by decreasing TP because T is constant. If you keeps on increasing this delta T, what will happen? This peak power keeps on increasing. Okay. And P average, we consider this entire energy within this entire time period T. So this is the reason why this average power is only 0.2 watt. While the peak power we are considering, main energy is concentrated over here, only this place. Okay, it is 0 for the rest of the time delta T. So this is the reason why there is a huge difference between the magnitude of peak power as well as average power. Okay. If there is any doubt, please let me know. Otherwise, I'm moving to the next topic, that is range equation. And that range equation analysis will do on the basis of analyzing the flow of energy from laser source to target and back to the receiver. Okay. So the next topic is to establish the relation between.
Sir,
Mhm.
sir, one question I have to ask, sir, regarding density across density. Sir, the distance between the two consecutive lines, is it the density across? Sorry,
Yeah.
distance across. Is it, sir?
Correct. Yeah, correct. See,
Okay, sir.
let's say this is the first scan line. Okay. And this is the second scan line. Okay. I've drawn here slant, though we consider it straight. Straight means this way we considered. Assumptions we have taken. So the gap between these two, these are the two successive points across the scan line. Okay, so this direction is called as across. This direction is called as along. And across the scan line, this is the aircraft is moving at a speed v over the terrain, just above the surface. So this gap, obviously this gap talks about if you take this in a vertical direction. So this gap is the distance between two successive scan lines. And this is the reason why the way we calculate the density across the scan line, it is equal to V divided by FASC, scan frequency. How many scans line covered in 1 second? It is given by FSC, and V, how many distance traveled in a second. Okay, it means the distance traveled divided in 1 second divided by scan lines covered in 1 second. It means how much distance is traveled if you are moving from one scan line to another scan line. This is given by this parameter. So it comes out to be D across, and 1 by D across is the line density across the scan line. Is it clear now?
Yes, sir.
Sumit?
Thank you, sir.
Yeah, you're welcome. Okay, so the next topic is derivation of range equation. So range equation talks about a relation between transmitted and received power. The transmitted power by laser scanner and received power. Okay. So to understand this, we have already derived, like let's just see. This is the laser source with a circular aperture having we consider this diameter dt, transmitter diameter dt. Okay. Through this, when this laser pulse emanates the transmitter, somewhere here at target point P, it hit the ground. At the same time, there is due to the diffraction, the laser footprint spreads around this target point P. And this is the total area within which the energy is distributed on the laser footprint. Okay. So this is the laser footprint. And this area AI, let's say total area illuminated around this target point, let's say P1, around target point P1, the total area AI that is illuminated by the laser beam or the pulse laser, it is calculated as, if let's say this diameter of this laser footprint, DF, how much we calculated DF?
So
This is
2
alpha by
R10
2.
plus DT.
Yes. And let's say this given this length is this, it is R. So it will be equal to this dt, that is diameter of the transmitter, plus 2R10 alpha by 2. If you take limit over here, limit alpha is very less. It can be written as into alpha by 2. Okay. As you know that 10 alpha, when limit alpha tends to 0, it is equivalent to alpha. Fine. So 2 will be cancelled out. And finally, it is replaced by R alpha. Okay. And area will equal to square pi by 4. Here this alpha is measured in radian. Okay. So this is a total area illuminated by the laser beam. And this area AI is area of laser footprint. Now we calculate power density within area AI. What will be the power density? So it is given by phi target. Its power density is equal to PT is the total power within the transmitted laser pulse. It's PT divided by total illuminating area AI. So how much power is striking within this area AI? So PT by AI is power per unit area AI multiplied by M. M is the atmospheric transmission. M incorporate like when this energy travels from laser source to target point P1, how much losses is there in the medium? It is quantified in terms of M. Okay. So M, the range of M is less than 1, less than 0. So it's a so PT divided by AI, total power per unit area illuminated by laser beam into M. It's a power density. It is calculated as a power density within the illuminated area AI. Okay. Now total power reflected. You can write it power density. Okay. Now the second step is what is a reflected power? P reflected. P reflected will be this surf when this point P1 around point P1, this entire surface has some reflectance. Okay. So the energy that is reflected back, that should be multiplied by, so there will be the concept of reflectance rho comes into the picture. Okay. Now power density is given phi target into a target. Let's say some target we are considering over here, and target area is obviously less than the laser footprint. And this within this target we have a point P1, and this is given by a target. Area of this target. So do you know, if you know that what is power density? This laser beams are this, I mean this energy within the laser beam is hitting this entire area, it is distributed. And if you have calculated the power density, then phi target into A target will be how much power will be reflected back in upward direction, okay? From this A target area only. Fine. If you multiplied by rho, it means you have multiplied with the reflectance of this surface. And again, you need to divide it by pi. Okay. Because see, so this reflected power per unit solid angle. You see, once it is reflected, it is a diffuse reflectance, so it will be in all direction, not in one direction. Like it will be in all direction from a target area. Okay, so you need to divide it by so that per unit solid angle, how much power is reflected back from a target. Okay, so it is given by rho multiplied by phi target into a target divided by pi. Is there any doubt? I'm giving you 5 minutes time. Please see these equations and let me know if there is any problem in understanding how we calculate phi target, how we calculate reflected power per unit solid angle. And you can
So
also
what
make
is this relation between this area target area and area which a collimated laser beam will make? Will it be same or any difference will be there?
see generally what we consider that target area should be less than this target area should be within the laser footprint. Okay. But if you
Okay,
see
sir.
that when we'll simplify this equation, we generally consider them equal.
Yes, sir.
Okay.
Sir, please could you one more time explain the P reflected, how this equation has been formed?
Okay, so I hope it is clear now. Okay, so P reflected gives us the reflected power per unit solid angle. Okay, so here if you see this A target is calculated as phi, that is pi target is square divided by 4. So D target is the target diameter. As you can see over here, this is given by D target. Okay. Again, when the same path will be followed by the reflected energy to reach this receiver. Okay. Again, this reflected power will be multiplied by factor m, that is atmospheric transmission. So that signal, that energy within the laser pulse travels from laser source to target. It is multiplied by m, that is losses. Again, the return signal is traveling through the same medium. So again, you need to multiply by again you need to multiply it by this atmospheric transmission m. Okay, so power received at the receiver, if you want to calculate is received power at the receiver, so then it is equal to the same this term multiplied by m. Okay, now it will be collected at the this antenna that is attached with the receiver. So that has size, let's say diameter uh, D receiver if it is given. Though we are calculating is per unit solid angle, so it will be multiplied by the area of the receiver divided by again the range r square. So we multiplied a r divided by r square. Why it is so? Because this parameter is per unit solid angle, how much energy is, how much power is reflected back. So when you talk per unit solid angle, and if you want to convert it in the area term, per unit area, so you need to multiply it by factor 1 by r square first to convert it into the area. And AR is the receiver area at which this energy is collected. This, so ultimately the received power, if you write the final equation, so received power is equal to m square. It's, if you see from here, 2 times into rho. These two are the constant, atmospheric transmission as well as the reflectance. Then you have a factor transmitted power PT. Okay. Then you have a target into receiver area divided by r square into pi into, again it's illuminated area AI. Okay. I ask you to simplify this. This like A target, it can be written pi by 4 D target square. A receiver area can be written pi by 4 dr square. AI can be written pi by 4 dt plus r gamma whole square. Simplify it and let me know. Dt is given, dr is given, and this for A target, let's say D target is given. Okay. Simplify it and let me know the simplified equation. Do this calculation at your end. I'm giving you 5 minutes time.
हेलो सर।
बताओ।
सर डी टारगेट और इल्यूमिनेटेड डायमीटर को बराबर ले लें।
You can take it equal. So in that case, this equation will be simplified.
ओके सर।
First solve it without taking them equal. Okay. Then you will get an expression. When you take equal, then uh, in that case, this equation will be further simplified. Okay.
यस सर।
Okay, so I hope you have derived the simplified equation by substituting these values for a target, AR, and AI. Have you done it? Okay. So the power received at the receiver is equal to reflectance multiplied by atmosphere square of atmospheric transmittance, and then the receiver, it's the square of diameter of receiver into square of diameter of target. Okay, divided by 4r square into the diameter of laser footprint whole square into pt. Okay, we can assume that this area illuminated by laser pulse, illuminated area is equal to a target. It implies that so in that case this diameter can be considered as equal to this. This will cancel out. Okay, and in that case power received at the receiver is equal to m square, this is receiver area, divided by pi r square into pt. Okay, without assumption, if you solve this in this case, let's say this is equation second. Okay, like equation one we have already considered for calculating this area, illuminated area. So if this is a final equation, it is equation 2. In this case, what happened, like r gamma plus dt, it is equivalent to r gamma because see dt is very less. The transmitter diameter is very less. So it is r gamma. If you replace it over here, in that case, what will happen? From equation 2, the received power is inversely proportional to fourth power of the range. By using this equation, it comes out to be fourth power of the range. It means if you increase the range, in that case, your power will be decreases. Okay, in a manner of like 1/4. Okay, it's not 1/4. I can say like it is 1 divided by r to the power 4. Okay, so if you increase the range by 2 times, and it's 2 to the power 4, 16 times your power will decrease. Okay, so this is the reason why we see when we do the analysis, if you increase the range, then the power at the receiver becomes weak. Okay, so this is the reason why we have a restricted flying height. We can't increase beyond that. Reason is that the signal that is received at the receiver becomes very weak in case of large range value. Okay, What other analysis we can have on this, on the basis of this formula? Like in the received power, we have a effect of reflectance, atmospheric transmission M. Reflectance has also its effect. Let's say if reflectance is only 20%, it means it will be 1/5. And if reflectance is 80%, so 20% reflecting target, 80% reflecting target have a different power. So for the same PT, all other parameters are same, okay? But the reflected will be, the power received at the receiver will be less. Try to see this equation and let me know if you have any other conclusion. Do the analysis, we'll have a discussion. Let me know, is there any doubt in this equation? And I hope all of you have derived it in your notebook. Shivam, could you please unmute?
Yes, sir.
This equation is clear to you?
हाँ सर, थोड़े आज नेटवर्क ब्रेक हो रहे हैं सर, तो मैं एक बार वीडियो रिकॉर्डिंग देख के सर.
Okay, please mute. Alok Kumar.
Yes, sir.
Is there any doubt in this equation?
No, sir.
Okay, so this equation can be, the simplified version can be written into two forms. The first one by equation 2, where you assume this diameter is equal to r gamma. And the second will be in terms of this, when you consider this, the illuminated area AI is equal to a target. Fine. So in this case, this is the simplified version by this assumption. And in the first case, the simplified version by considering this, the laser footprint diameter is equal to r gamma. So this is given, the final power that is received at the receiver is equal to this rho atmospheric transmission square into the multiplication of this receiver area pi r square into this is the peak power transmitted by the peak power transmitted power from the laser source. Okay. So I expect you have derived, you have written the steps in your notebook. Go through this and try to see, like I will share with you a reference notebook, this reference material, where the certain values are given for these variables. And once you substitute for the real system, the values are given for a real system. If you substitute over here in this equation, you will get the received power value. This will be very low. Okay. So by using those values, do the calculation and just see that. Okay. For the real system, what the value we select for this transmitted power. Okay. What is the effect of atmosphere in terms of M? What is the size of this receiver that we consider over here? Okay. And by considering all these values, what is the received power at the receiver?